So this lecture serves as a very brief introduction to drinking water treatment. We've completed wastewater treatment now, and as I mentioned when we were talking about that, some of the same processes are present in both wastewater treatment and drinking water treatment. So for example, disinfection, we will not have a separate lecture on that because a lot of the same stuff applies. I'll just mention where there's some little differences. But with drinking water treatment, our goal is to produce a safe and palatable water supply. Untreated water, these are some tables from your book and what untreated water contains. So you've got major inorganic constituents. So these are typically things that we consider like maybe salts or major ions, typically present in the crust of the earth. So in rocks and minerals, calcium, chloride, fluoride, iron, manganese, nitrate, sodium, sulfur, large concentrations of these. You've also got minor inorganic constituents like trace metals, typically present at 3, 4, 5 orders of magnitude less than that, but still very relevant for things like toxicity. We've got naturally occurring organic compounds. So natural organic matter, total organic carbon, this is like decomposing leaf litter or organisms, bacteria. These are living things or previously living things. Then we also have anthropogenic organic constituents. So these are generally small synthetic organic chemicals used in pharmaceuticals or chemicals, pesticides, that sort of thing. And then living organisms, bacteria, algae, and viruses. There's lots of those. Then we have come to this table on physical characteristics of water. So we've talked about some of this in the water quality lecture, but turbidity is one, and color that I want to just talk about a little bit, particles as well. So turbidity just measures the light scattering potential of the water, and how is that really related to how safe drinking water is to drink? Well, it doesn't really matter from your body's perspective how much light the water scatters. That measures the optical clarity. But turbidity is used as a surrogate for a number of other things. If your water's pretty turbid, it probably has bacteria and viruses that you don't want to be drinking in it. But if it's very clear, it probably doesn't have as many of those, right? So the World Health Organization has a turbidity of less than 5 NTU, which are these nephelometric turbidity units, is usually acceptable, but can vary depending on how you treat the water. In the U.S., we're typically less than 1 NTU. Even in wastewater, when you're using UV treatment, you need to have the NTUs less than 2. Drinking water less than 1 is very common. Basically, we can't see that there's any turbidity in water until you're at least 5 NTU, if not closer to 10. Again, it's just a surrogate. We can measure turbidity pretty easily, and it's a surrogate for how well have we treated the water. Same with particles, same with color. For example, the color of water doesn't really mean anything in terms of our body, right? The health of the drinking water doesn't depend on the color, but the color is a surrogate for other things that could be in the water that are maybe harder to test. So in drinking water, there's a lot of that kind of stuff that we do because we can't measure every single one of all the things that could possibly be in water. Taste and odor, and then temperature, other physical characteristics of natural water. So Safe Drinking Water Act regulates drinking water. We have what are called primary MCLs, or maximum contaminant levels. These are limits, criteria that have been adopted as water quality standards that protect human health. So, for example, if nitrate has a primary MCL of 10 milligrams per liter as N to protect against the acute effects of blue baby syndrome. But there's also secondary MCLs, which are about making the water supply palatable. And so these typically have to do with taste or odor or aesthetics. So for example, there's a secondary MCL on color. There's a secondary MCL and chloride to protect against taste. So these guys are a little bit more important because they have to do with human health. These ones can be more relaxed in certain situations and on a temporary basis. Depends on how the states adopt these criteria. Okay, so unlike with wastewater treatment, where what's coming into the treatment facility is pretty similar across the world, right? It's domestic wastewater. It looks about the same wherever you are. In drinking water, depending on what your water source is, what you need to treat looks very different, and thus your treatment process can look very different. So these are some treatment trains from your book. This first one is maybe what I would consider a conventional surface water treatment system. So you have influent from surface water, like a river or a lake. You've got some screening, some pH control, some disinfection, chlorine, for example. And then you've got this coagulation, flocculation, sedimentation step, some polymer, a filtration step, more chlorination, and then discharge to the distribution system. And then the solids that you're removing from that water down here. And this is all necessary because in a surface water system, you've got particles that need to be removed. And so this coagulation, flocculation, sedimentation step, filtration, all designed to remove particles that are in the water. Both because we don't want those particles in the water and because there are microorganisms that can be attached to those particles or be particles themselves that we don't want to be in our drinking water. Versus a groundwater system, a system that is getting its water from groundwater, might look a lot like this, but without anything prior to about, say, here. Right, so all of this isn't needed because the ground itself is acting as a giant filter. So once you get to the well, you don't have particles anymore. And thus we don't need all this particle removal stuff. All we really need is disinfection. Now, you could, so that's what these two lines say. Now, if the water contains a significant dissolved constituents, you could add unit processes to address those. So, for example, in the city of Newburgh, we have a groundwater system. Wells provide drinking water to the drinking water treatment plant. And in theory, all we would really need is chlorination and maybe some pH control to protect against corrosion in the distribution system. But our groundwater tends to have a lot of iron. And so there's a whole process that kind of looks something like this, where polymer is added and it's allowed to sort of flocculate with the iron, form bigger particles, and then be filtered out. All that iron sludge is filtered out before it goes into our drinking water. And thus the water in our homes doesn't have as much iron, so we don't taste it as much. Our fixtures and our laundry aren't stained by that reddish color that would be in the water. You could also have like high hardness is another one, so there could be a central softening plant where the water is softened, hardness is lowered before it gets put in the distribution system, so things like that. The one on the bottom here is a membrane plant. So it looks kind of similar to above, but instead of these three processes here, coagulation, flocculation, filtration, to remove particles, we just have maybe some pre-filters and then membranes, and then this is a reverse osmosis, which is also a membrane process. So again, these are designed to separate particles from the water. It's just a different kind of technology. So very, very high quality drinking water sources, if it's required to bring the water up to a very high quality, or if it's desalination, you would need a membrane facility for extremely high quality water. And that can also remove, if you're using things like reverse osmosis, you can remove some of these anthropogenic organic constituents which wouldn't typically be removed to a very high degree in a process like this one. So as we go into drinking water treatment, we'll spend a day talking about these steps right here, how you would design filtration systems, how you would design and analyze coagulation flocculation systems, what are the processes involved in that. You can see here that there's no biological processes in a plant like this, like there is in wastewater treatment. And so we can add the chlorine, the disinfectant, right at the beginning of the process. And all the time that the water spends in these processes, we can be getting that chlorine contact time that we want. And then maybe we add a little bit more at the end just to make sure we have enough residual chlorine in the system before we put it in a distribution system. We can't do that in wastewater because we have a biological system we don't want to interfere with. So we can't add the chlorine at the beginning of the process like we can here. A good thing about doing this is you keep a lot of these processes fairly clean, and you don't have to clean them out as much because the chlorine can keep them clean. And then we'll spend another day talking about membrane processes, desalination, reverse osmosis, nanofiltration, ultrafiltration, microfiltration, those kinds of things. So that's just a brief intro to drinking water treatment, and this, as well as the wastewater solids handling lecture, is it for today. Don't forget to take the quiz. See you next time.